Data is a collection of facts. Unstructured raw numbers are a mess. First, line them up in ascending order. Next, build a frequency distribution table with item, tally, and frequency columns. Draw 4 vertical lines. The fifth strikes diagonally, creating a bundle to count instantly. Grouping numbers turns raw chaos into a countable summary, showing exactly how often values appear. But to spot patterns instantly, we need to translate these numbers into pictures. This is a pictograph, and it uses symbols to represent data. Whenever you look at one, you must start by checking the key at the bottom. Here, one book icon does not mean one book. It represents 5. To find the total for any category, you simply count the symbols and multiply. 5 icons in a row, multiplied by the key of 5, tells us exactly 25 books were borrowed. But this system breaks down when the numbers get complicated. If your key states that one icon equals 10 students, how do you show exactly 33 students? 3 full icons give you 30, but how do you draw exactly 3/10 of a person? You can't. Drawing precise fractions of a symbol is nearly impossible. When dealing with large or highly specific numbers, pictographs lose their utility, and we have to rely on a more precise tool. This chart is a bar graph. To maintain strict accuracy, a bar graph follows 2 requirements. The bars must be of equal width, and they must have perfectly equal gaps between them. Instead of counting individual icons, you read the data by looking at the height. By tracing a line straight from the peak of the bar over to the vertical axis, you lock in the exact number. Constructing your own graph presents a specific challenge, choosing the right scale. Let's say you have a data set where the maximum value is 13. If you make one unit equal to one item, you have to draw 13 individual hash marks, which might make your graph too tall for the page. Instead, you can compress the scale. If you group the markers by 2s, the exact same data fits comfortably into half the space. To plot an odd number like 13 on this even scale, you don't need a new line. You just bring the top of the bar exactly halfway between the 12 and the 14. By adjusting the scale to fit the data, you map any set of numbers onto a page, maintaining perfect mathematical precision without running out of room. While vertical bars naturally represent heights and horizontal bars show lengths, poor design choices can easily distort the facts. Let's compare 2 real-world values. First, Mount Everest, with an elevation of roughly 8,850 meters, and second, Mount Elbrus, which stands much shorter at just over 5,600 meters. If we graph this comparison using triangles, watch what happens when a designer tries to make Everest look more dramatic. If the designer doubles both the height and the width of the Everest triangle, they artificially balloon the total area. Mathematically, it should only be 1.5 times taller, but it visually looks 4 times larger. To keep the comparison honest, only the height can change. Keeping the base width identical for every bar prevents the area from exactions into structured tables and graphs, ensuring that the proportions stay accurate and the numbers remain easy to read.